Welcome back, scholars, to our first installment in our new unit on polynomials and rational functions. It is jam-packed, so let's get into the nitty-gritty. Today we're going to learn to comprehend that when polynomials are combined by addition, subtraction, or multiplication, the result is a polynomial. So I can identify the relative minimum, maximum, degree, leading term, and constant term of a polynomial. I'll know I've got it when I can identify important characteristics of polynomials, graphs, and expressions. Some of the vocabulary words may look familiar, which will only aid us in our exploration. So on the first slide, you have 4 different algebraic expressions on display here. Please select the one that you think does not belong and explain why. Some vocabulary before we segue on to our next slide is a polynomial function can always be written as a sum of terms, each of which is a constant times a whole number power of x. Define the degree of a polynomial to be the largest exponent on a variable in a polynomial, which is one way that polynomials are classified. So in the case of our first expression here, we would say that this polynomial is a degree 3 polynomial because the highest exponent in this instance is a 3. In this slide, you are tasked with sorting the cards into pairs that represent the same polynomial function. A hint is that you can strategically eliminate graphs by testing specific x values to see if the output of the function appears to match the y value of the graph. Case in point, y equals -15, and this horizontal line, there we go, have the same behavior because y is equal to -15 no matter what value of x we select. So I will give you an easy pair there. We are at the exploratory phase of our unit since we are just starting out. So be patient, persevere through this. If you're unable to match all of the cards, that's totally okay. We'll talk through some of those strategies in class. You would have noticed in the previous slide that some of our graphs have very, curve-like behavior to them. Since graphs of polynomials can curve up and down multiple times, they can have points that are higher or lower than the rest of the points around them. We define these points to be relative minimums and maximums. Since we're still playing in the sandbox, on the following slide, we're going to construct equations for polynomials whose graphs have the characteristics listed when plotted on the coordinate plane. What do I mean by that? So as you can see here, we have a bunch of different descriptions. For instance, in g of x, we need to construct a second degree polynomial function whose graph has only positive y values. So to create a second degree function, my highest power would need to be x to the second power, but I only can have positive y value outputs if I drag along my graph. Everything seems to be positive except for the vertex, which is 0, and is technically not positive or negative. So if I want to raise my graph, I could add a constant, and now my graph has completely positive y values. So the good thing about technology is you have an opportunity to revise and edit your thinking after you get some instantaneous feedback based on your equation. So you have 4 other criteria to satisfy before proceeding on to our next slide. I would like for you to have a conversation with your peers as it pertains to the different strategies that you use for changing equations to meet the specific criteria. What did you come to realize? Such as adding a constant. What does that do to the overall graph? Or what happened when you changed the degree of the polynomial from 2 to 3 or from 3 to 4? Were there similarities? Were there explicit differences? Let's generate a nice little discourse going before our time together in class. In our table, we have some various criteria, and it is your job or responsibility to determine if this criteria is valid. Can the graph of a polynomial have a loop? Right. So does that mean, can it have a circle within its graph? Is that valid or invalid? If it's invalid, please make sure you provide some evidence to support your claim. Does y equals 3 count as a polynomial? What degree does it have if it does count? Can the variables have negative powers? Is a single number like 10 a polynomial? Do the coefficients have to be integers? Do you think that these are traits, qualities that are representative of polynomials? Yes or no, and explain why. Oops, double clicked. In our final slide, we're going to do a little bit of experimentation. If you add or subtract two polynomials, will you always get a polynomial? If you multiply them, will you always get a polynomial? What is difficult about doing arithmetic on polynomials? How did you deal with this difficulty? What do you think would happen if we divided one polynomial by another? Would we get a polynomial? All the time? Sometimes? Never? I encourage you to construct your own polynomials, right, using our square root button and performing the algebraic operations being described before you. That way you can kind of visually see the mathematics at play and come to a conclusion regarding whether or not the questions are being satisfied. Once again, we're in lesson 1, so we're exploring, just kind of getting our feet wet. No real legitimate foundation yet. We're kind of creating that, so to speak. So that's where we're going to pause, and we'll pick up our discussion together in class.